Thanks everyone. I really appreciate the opportunity. Thanks for the introduction, Derek. I was really hoping to be in person down in Melbourne for this conference, but unfortunately things didn't quite work out that way. And apologies if I get an interruption any part of the way through this. I've got a sick kid at home as well. So, as COVID has changed everything, hopefully everyone's used to that by now. But today I'm just going to be talking about my thoughts on AI or ML and whether aviation truly can coexist with that. So I suspect that some of the things I'm going to talk about today have probably been covered by various presentations, and unfortunately, like I said, I wasn't there to see who's presented what so far. So again, apologies if I double up on some things. Hopefully I don't say too many things that conflict with what has been said already, but there's probably going to be a few things in here that are a little bit different to maybe what is expected. So let's get into it. All right. So just before I get into the content, really quick overview, background of myself and the team at Revolution Aerospace. I spent around 10 years in the RAF, where I learned my aerospace engineering trade. As Derek mentioned, I worked for Derek through part of that. I moved on to Nova Systems back in 2013, where I spent a significant portion of my time working on uncrewed aerial vehicles or drones and UAS traffic management. So recently, it's nearly a year now, I finished up with Air Services Australia, where I shaped Air Services direction for future airspace management, inclusive of UTM, stratospheric traffic management, and advanced air mobility. From August last year, I've been working full-time as co-founder and CTO of Revolution Aerospace with Dr. Terry Martin. And Terry sends his apologies as well. This was supposed to be he and I talking, but unfortunately, or fortunately, he's in Cologne in Germany right now, living it up. Well, maybe not living it up, we're still a startup, so no business class flights for him. But he's over there for a JARIS conference, which I'll talk a little bit about later on as well. But we founded RevAero with a vision of benefiting society through revolutionary advances in autonomous systems technologies. We're leveraging our technical consulting experience to develop autonomous systems tech. So we're not just consulting, we're actually developing. And we've started to assemble an amazing team, and we're at 9 strong right now after less than 12 months. So that's RevAero. About this presentation, right? So there's probably a bit more opinion than hard fact in what I'm going to put forward today. So hopefully that's not offensive to too many people. But hey, I am from the world of software assurance, where a lot of it is sort of, it's not empirically based. It's a lot of, really smart, intelligent people putting together consensus ideas and standards on what seems to be sufficient to deal with the complexities of software in the aviation sector in particular. It might be a little bit philosophical at points, and there's probably going to be a fair few generalizations, but hopefully there's some good things to think about at least. I'm going to talk through the challenges, and with challenges always comes opportunity with AI and ML in aviation. I'm going to pose the question of, is aviation software actually deterministic like we all kind of assert and talk about? We'll also look over how is everyone dealing with complexities such as non-deterministic AI and ML, whether the approaches that are being taken at the moment are going to work. Again, opinion, not fact, and a little bit of future gazing. So some challenges and opportunities. Well, and like I said, apologies if you've been over this already over the last week, but just a little baseline activity, I guess. AI and ML technology has advanced rapidly, while the aviation sector is traditionally very incremental and moves very slowly. Probabilistically characterized technologies are proving to be highly effective in various niche, maybe sometimes in more generalized areas, but typically, the application of AI and ML as it stands today, it can be very effective in certain applications, in certain roles and limited kind of circumstances, particularly in things like detection and tracking. But more generalized, it becomes quite challenging and very, very complex. There's a massive amount of investment, which is driven by a massive amount of hype in the industry. That is just generally across AI and ML. And that's what has generated a significant amount of movement and advances is the hype, which is simultaneously a good and a bad thing. And in some cases, AI and ML can be vastly more capable for automation of certain tasks compared to traditionally human-controlled tasks. Again, a generalization, but it is a possibility. But the problem is, for all of us in the aviation sector, it isn't deterministic. It's probability-based, and it's hugely complex. And complexity is pretty much the enemy of all things aviation software and system safety. Does make for a good challenge though. So in terms of not being deterministic, they aren't, AI and ML aren't for the most part. Decisions and actions are made based on probabilities. So I've mentioned classification before, so classification of signals, automation based on the probability, that's the automation of activities, whether it's classifications or decision making based on the probability of detections being correct, and that's susceptible to miss rates and the false alarm dichotomy. If you've heard Terry speaking before, you'll those few phrases will be pretty familiar to you. The learning process itself is highly dependent on the data being representative of reality. So that's for your training set and your testing set. How close to reality is that set for the training of the machine learning algorithm and the testing of it to verify, that it's doing what you want it to do, and therefore the probability of it working? Is it actually, closely tied to reality, or is it generalized, or is it, maybe too much of a restricted set? Some of the hype that comes along in this sector, and particularly around statistics. I'm not sure if any of you have seen this recently, but Tesla released some statements about, well, I don't think, actually, let me get this right. They did not actually say that their autopilot is 10 times safer than average cars, but obviously, the media extrapolates those kind of statistics. However, what Tesla has done is put out, information that sort of says, here's what we've achieved in terms of crash rates, accident rates. And then they compare that accident rate where they have autopilot engaged with an accident rate for the whole, whole data set that the NHTSA holds. And that accounts for all phases of driving and operation of a vehicle. So what's happening here effectively is someone's extrapolating for a narrow kind of statistic focused on only when autopilot is used, comparing that with a generalized statistic for all cars in every kind of operation. And realistically, it's just not an apples to apples comparison. When you're using the places where autopilot works pretty well and where people tend to use it is on open roads where the quality of the road is good, the line markings are good, speeds, are a challenge, but generally traffic flows where it should, and there's not many obstacles. So it's one of those things where, it's very easy to throw out the numbers, but what do the numbers actually mean and how do you interpret them? You may have seen this around as well when it comes to anything AI or ML based, the 90, the 95, the 99% accuracy comments. But what do they mean in reality? When you actually look at those numbers, it's very easy, again, to throw the number out, but how do you interpret that in terms of, 90% accuracy to what, in what environment, and how was that determined? A paper I read sort of talks about, here's how we get you from 50% accuracy to 90% accuracy. And all of the suggestions made, are all about just throw more data at it, more layers at it, increase your image size, do more epochs, use less color channels, and maybe transfer some already trained models from another domain to your domain. And there's so many flaws with that thinking. It really comes down to bigger is better, and steal what's already been done from another application. We all know about Ariane 5, so maybe that's not the best way of doing things. The number that usually is used to represent accuracy of machine learning trained algorithms is the mean average precision, and that number is entirely dependent on the data set that's used, and again, whether or not that data set actually represents reality, or a real real application, is kind of the question there. So in terms of verifying the accuracy, essentially you train your model on a set of training data, and then you test the model on a different set but the same kind of data to determine how much of the training of the verification set was actually correctly identified or captured. It all comes to bad data in equals bad data out. If those sets are not great, if there was only 10 sharks in the set for verification and it detected 9 of them, that's not a statistically significant test. And also, were the sharks like in clear daylight, in just below the surface of the water where things were easy to see? Does that mean it's going to work well in real life? And yeah, there's the famous saying, lies, damn lies, and statistics. It all comes into how things are promoted with AI and ML. And don't get me wrong, I'm not against it. I'm all for ML and AI having a significant role in the aviation sector, but we need to make sure we understand what those numbers mean when they're thrown out there. So just a summary of the challenges: we've got the hype in statistics, the non-deterministic aspect, and ultimately it kind of all drives to complexity. But is there really anything different in complexity that we've not experienced before? I mean, we've gone from canvas-covered aircraft to highly software-intensive autopilot and flight control systems. What's different? Is it something that we've dealt with before, and can we continue to? We'll come back to that in a minute. All right, so this is where I probably get a little bit controversial. Is aviation software really deterministic? Well, I guess the question I'm really posing is, are we confident that it's deterministic? And for anyone who's familiar with the matrix, is there actually a spoon? Or are we putting a lot of faith potentially in something that may not be hard fact? And does it matter? So when we look at the traditional model for aviation software, which we're claiming to be relatively deterministic once we're finished with all the activities we normally do for software safety and software assurance, we look at how severe are the consequences of a certain failure of a system in the context of an aircraft, and we apply a bunch of software safety or generalizing validation and software assurance, again generalizing into verification, basically to try and reduce the probability of unsafe requirements and errors in the development process. So no probability there. So yes, we're trying to make it as deterministic as we can, but it's still a probability game. Building systems, it's inherently a human endeavor. Automation is inherently reliant on humans to dream up how we can do these things safely. And there's really nothing deterministic about that. I mean, we do try to reduce the level of uncertainty and therefore the probability. So we're aiming for determinism, but there's nothing that guarantees outright determinism. Hardware failures in themselves are inherently probabilistic also, and random failures are randomly distributed. So looking at those boxes on the left there, this is kind of a very high level summary of some assurance and software safety activities we might carry out for a traditional aircraft or system. We look at trying to reduce the probability of bad requirements, and even formal methods. Formal methods are susceptible to bad requirements. We look at the probability of we look at reducing the probability of erroneous traceability, erroneous code, and we acknowledge, sorry, there's a space there that shouldn't be, The inability to exhaustively test means, back up to number 3, there's probability of erroneous code that exists, and so on. It continues. So when it comes to determinism, algorithms and design can be deterministic. Math is pretty black and white. We can make stuff mathematically correct, but that doesn't mean the mathematically correct design or algorithms are deterministic once embedded into the system. We can get it wrong, and we sometimes do. The implementation and verification process is the bit that isn't deterministic, although we get pretty close. And it is a human process. So whenever there's humans involved, there is a level of non-determinism built into how things are carried out. So I guess the question now is, how is everybody dealing with this at the moment, particularly when we look firstly at the traditional aviation sector? Well, there are some very limited applications, and I'll talk about just briefly one that was certified this week, so I'm not sure if it's come up in other presentations or not. But very limited is the key there. It has been done, but not much, and it's in very kind of narrow areas as well. I think we're a while off before we see a flight control system that is based on machine learning or artificial intelligence. We do currently also deploy purposefully probabilistic subsystems in some cases. So TCAS, ACAS, XU, detect and avoid, each of those is probabilistic in nature in that they deliver an outcome that's, I guess, a functional outcome that is based on the probability of actually achieving the requirement of what they're supposed to achieve. And that probability itself is part of the functional requirement. None of them, though, in that case, are specifically AI or ML, except for the one that's coming up. I'll talk about in a second. So what do we look at in terms of how to deal with this non-deterministic probability-based problem? Well, in some ways we try to revert to air quotes deterministic software. That's kind of a very common and well-trodden path. One of the first one that sort of comes to mind is external monitors to confirm that this highly complex and non-deterministic software is still making decisions within safety limits. Like I said, it's a very traditional approach, high assurance, high integrity software as the monitor combined with a really smart architecture. I'm a huge advocate of this approach, and I think particularly in my time in the UTM field at Air Services, this was kind of the way I saw UTM ultimately playing out, where it's delivering a safety function, really digging into how to architect the system from a safety perspective to partition out the really highly critical functions and monitor those functions versus necessarily having to assure the whole system. But it probably won't solve all the problems. We get to the situation where potentially the monitor can become as complex as the AI that it's trying to monitor for it to be effective. And that's obviously not the right answer. Multiple version dissimilar neural nets is another concept being thrown out there. I don't think this is actually doesn't solve the determinism problem, and in terms of being certifiable in the traditional sense, it's probably going to be a challenge. But it does provide an increase in confidence that between these multiple version dissimilar neural nets, that the outcomes that each of them are, or the outputs that each of them are delivering, are at least the same or correct, or that there's some issue with what's coming out. And this would probably extend to the training and verification sets as well. How dissimilar do they need to be for the actual algorithm to be considered dissimilar? Another option is to revert to deterministic software in these degraded modes. However, that still relies quite substantially on these external monitors being able to monitor for those situations where the complex non-deterministic software has been deemed to have failed or given an incorrect output. So when it comes down to it, there's no, until early this week, so I probably should have corrected this slide, but there's no real significant guidance on how to certify machine learning or AI against standards that we currently use in this sector. Some of the most recent developments, however, this is what I was mentioning just before, EASA, I think it was last year, sort of put out a couple of papers on the concept of design assurance for neural networks. And they referred to this as learning assurance. Effectively, the approach was to sort of look at how do we break down the requirement set, the implementation, the learning process, and the verification that we normally see in a V model to sort of fit this, how you create machine learning algorithms. And what they come up with was the W model. I do wonder if they could have just put the learning process verification down the bottom and it still would have been a V, but whatever, it's a W. It's, I guess the whole intent of that is to try and, again, remove some of the uncertainty, make it less non-deterministic in terms of how the whole algorithm was pulled together and trained and verified. Not just earlier this week, so the 24th of May, the FAA produced a paper called Neural Network-Based Runway Landing Guidance for General Aviation Autoland. A company called Daedalus, who was also behind the EASA work, they've claimed, I'm not sure if this is actual fact, it seems like it could be, that they have the first DO178C certified vision-based machine learning algorithm. Now that's at Daedalus. What I do wonder, and this is again trying to fit it back into the old model, whether or not they'll be successful in proceeding from Daedalus to any higher, because as soon as you start bringing around traceability from source code through to machine code to the executable, I haven't looked into it in depth, but I imagine that's going to be hugely complex when it comes to a machine learning based algorithm. So, as I said, basically, this whole process is about trying to make it less non-deterministic and have more confidence that outputs for a given set of inputs are repeatable. I guess the bigger, broader challenge I see with all of this is Augustine's 16th law. So tongue-in-cheek, but when you start thinking about it, maybe there's a lot of truth to this. Basically, says Augustine's law says in the year 2054, the entire defense budget, US defense, will purchase just one aircraft. The aircraft will have to be shared by the Air Force and the Navy 3.5 days a week, except for a leap year, where it will be made available to the Marines for the extra day. Now, the image on the left sort of gives you that feel for where things have sort of trended over the past 100 years. And that there is probably an element of truth in Augustine's law. It's based on some of the observations in the past, and it does seem that year on year, every major aircraft design, acquisition, production kind of project takes longer and longer and longer and costs more. So at the moment, it seems that our solution to complexity increasing exponentially with AI/ML is to add more requirements, more methods, more checking, more effort to the certification process. There's not a whole lot of how do we reduce potentially the overhead in carrying out this, this building of confidence. And that becomes a problem because it just doesn't scale into the long run. So, maybe the automotive industry's got some ideas that could be leveraged, although, these are kind of sort of probably frowned upon, I would say, a little bit in terms of how the aviation sector sort of views system safety, software assurance, and software safety. However, as an example, detection and tracking is inherently a probabilities game, and wherever there's detection and tracking deployed, whether that's ATC, primary radar, adaptive cruise control, computer vision, etc., it's all based on how how probabilistically, how correct is your solution going to be probabilistically? How many misrates? How many false alarms? Where do you sit on this ROC curve or DET plot? You can choose to detect a lot of stuff and potentially provide lots of false alarms, or you can choose to not detect many things, but don't annoy the driver too much, or the system too much. So, autonomous vehicles or highly automated are very reliant on ML, particularly when you compare it with aviation. So what do they typically do? Well, the complexity of an autonomous vehicle's guidance control system is, if not more complex than anything in aircraft, it's way up there. Multiple sensors combined, fused together, pass through a neural net for detection and tracking, and potentially another neural net for how to respond to those things. The outcome being inputs to throttle, braking, and steering. It's broadly considered, this is again a generalization, broadly a black box that in some instances, some companies put into massive simulation and simulate billions of miles of operation to test it and understand how it responds. Now, that doesn't get us away from the fact, the question of how good is the simulation, but it is what a lot of them currently do. So in the aviation sector, this is kind of where we're sitting in terms of how we deal with it. Only just last week has some really good guidance been published that resulted in certified ML. There's lots of research and effort to come up with more solutions for this, but it's still coming. In the aviation sector, the solutions really come down to trying to shoehorn non-deterministic software back into our deterministic so-called framework. The problem with all of this that I see is just increasing certification overhead for increasingly complex software. So, let alone functionally complex software, we're adding onto that and increasingly complex certification burden. And I'm not sure that scales into the long run. It's going to bring with it big challenges. So the question is, do other industries potentially have an answer? And we look just briefly at the automotive industry just there. So looking to the future, well, originally when I was putting this presentation together, I had asserted that maybe there's a bunch of stuff from the US sector that we could leverage for our traditional aviation sector in this space. Now, I have to admit that's probably not the case. However, there are some aspects of UAS and how things are currently dealt with that provides an avenue for some things, but not all things. So effectively in the UAS sector, we've got this concept of the Joint Authorities Regulation for Unmanned Systems, Specific Operations Risk Assessment. That's a mouthful. It's a model or a framework for approvals or determining the safety of UAS, but it's still maturing. It deals with essentially the lower risk portion of UAS. So effectively, if a UAS isn't going to be certified or considered the same kind of risk level as a Part 23 or Part 25 type aircraft, how do you approve things below that level of risk? And that's what the SORA is all about. So the standards underpinning many aspects of the framework don't yet exist, or they're sort of being worked on or being pulled together at the moment. In some cases, the requirements to approve technical components of the UAS, however, they don't necessitate formal software assurance standards. So there are some options in that framework to approve lower risk kind of systems and software and hardware in a way that is far more qualitative and more reliant on system level testing. An example of that is the EASA means of compliance for enhanced containment for low risk operations. So effectively, if you are trying to approve an operation of a UAV in an area that has quite a low population density, because we're concerned about crashing into the ground and who's there, and low encounter rates in the airspace, then there is options to contain your operation to that airspace and over that part of the earth, and approve that containment system in a much simpler way than what we might necessarily do for much more complex software. So that exists as an option. However, as soon as you start stepping beyond those more qualitative confirmations, and in some ways, that's kind of similar to how we deal with light sport aircraft, for example, it really falls back to how do we, can we deploy this really smart architecture, monitoring, and sort of graceful degradation and failover methodologies. That's kind of where I see things continuing to head, is breaking down the system such that where the really, really highly critical stuff is, and pushing everything else into being monitored kind of functionality. We do that traditionally with aircraft, but I think it's more of a we just need to step it down to the next level to really get into the weeds on that. So hopefully this isn't heresy, so please don't burn me at the stake for this one. But I sort of mentioned it before with regards to the autonomous vehicle sector. How do they do things at the moment? Relying on, I guess, testing in its own right, just testing and not considering design assurance, it has really been frowned upon as a means of demonstrating software assurance. However, and that's not to say we shouldn't be looking at the design assurance aspects, the requirements, traceability, all of that kind of thing. But is more generalized testing, acknowledging that it still can't be exhaustive, something that we should really be exploring in a more robust way? When it comes to DO 178, for those of you familiar, everything should be requirements-based testing. So we don't test things unless there's a requirement for it. And if we find parts of the software after testing that the requirements-based testing didn't exercise, then we know either we've got something that shouldn't be there, or maybe there is something that should be there but we haven't documented it and we need to go back and figure out why. Now that all makes sense if you know what the requirements should be. This is coming back to that sort of validation concept. So in this world of complexity and really complex machine learning and AI, maybe there's a need to lean more into that space of more generalized testing, possibly in a virtual environment and mixed with reality as well at the system level. Maybe it's more valid now than it has been in the past. So from a computer vision perspective, there's been massive improvements in visual data, the availability of that visual data, and the accuracy of the environment. So we're currently working on a low size, weight, and power detect and avoid system, and our approach is going to be heavily reliant on simulated airspace data and encounters and intruders and all that kind of thing. So I guess the progress that's been made in this industry has been quite significant over the last decade or so. And similarly to the way that I guess the military simulation kind of sector was disrupted from the gaming industry in terms of where all the processing power come from, that same industry has been really pushed by cryptocurrencies and mining, resulting now in even more capable kind of processing powers and capabilities, and the data sets and ability to simulate real environments just continue to improve. So there's a possibility that sort of gives us something that we didn't have previously. But we can all acknowledge simulation is also not the silver bullet. The complexity of the simulation, depending on what the application is, could very well be more than the non-deterministic software we're trying to certify. So again, if that happens, we've done it wrong. And for those very rare and high consequence situations, it's often really impossible to predict them. Things like single event upsets. How do we know that we'll actually find those kinds of issues through simulation? What's not as complex as modeling the real world, though, is potentially using the real world. So an option that we've got there is looking at parallel testing. So If simulation becomes too difficult, or we want to pair some real world testing with simulation, why don't we see what happens in the real world? Obviously, we don't want to hand over the keys to the AI and hope that it works. But how can we subject the non-deterministic software to the same inputs as another acceptable benchmark? Now, whether that be a human in some cases, or whether it be something that we trust more as deterministic or certified software, what decisions or actions would the AI ML based algorithms have made compared to that benchmark if we subjected it to the same input conditions in the real world? Now, obviously, you wouldn't want it to actually deliver the control outcomes, but you could quite easily monitor what it proposed as outputs and compare those with what was actually carried out. So another concept to consider in this this mix of things that may or may not be thought about in the right way. Largely, software assurance hasn't been the source of our major incidents. I'm sure everyone's familiar with Nancy Leveson. Getting the behaviors of the system right in the first place, she posits, is still and always has been and still is the hardest part of safety. But and I remember even my first few days in becoming a software safety engineer, that was touted as the big thing. We need to get the requirements right. We need to ensure everything's valid. That's the hard bit. But I still don't see a whole lot of effort being put into how that happens. So, as a generalization again, I think that validation of requirements is possibly more critical than the verification against them. We typically do verification pretty well, even though I would argue it's still not deterministic. We try to remove it, non-determinism as much as we can. But being able to carry out more real world testing, acknowledging that it can become economically very expensive, is probably the thing that's going to help us uncover all of these requirements that capture safe behaviors of the system that we may not have thought about otherwise. So wrapping all this up, I'm just going to give you a quick example of a use case that we're currently working on. So this low swap electro-optical DAA system. It's effectively, we're using a machine learning based algorithm for detection and then more traditional algorithms for tracking and maneuvering and alerting. But the broad approach we're taking, we acknowledge there is no silver bullet. Everybody understands that. And so it can't be solved with just get it out into the real world and test it. But certainly we think that some of those items that we've just talked through are all parts of the solution. But think that there is probably more of a benefit to simulated and real world testing than maybe previously. So we're adopting a traditional systems and safety engineering approach. We're using traditional software safety and assurance for deterministic software. Effectively, even though we hadn't dug into it that deeply, we are using similar concepts to the W model that was proposed before. So looking at data sets, construction and the optimization of those data sets, looking at the real data and extensive simulated data, and trying to get those requirements right for the type of model and the type of data, which is a challenge, but we're, I guess, leveraging real world experience, thinking and research to figure out, well, what is the right way to do this? And we're looking at sort of different training for below horizon and above horizon encounters, because the background clutter, for example, is very different in each of those. We're looking to embed monitoring functions throughout, and as I mentioned, extensive verification via simulation, statistically significant sort of amounts of trials there, and then a bunch of real world testing as well. The problem and the challenge with all of this is low size, weight and power DAA system for small UAVs. For it to be commercially viable, we need to minimize the overhead. It doesn't cost much for a Cessna 172 to operate with a pilot on board, and you can quickly exceed that kind of cost with UAVs if you can't get to the solutions in a to deliver deterministic enough software at a reasonable price point. Just one last thought, a thought bubble to sort of wrap things up as well. There's a question of how much certainty in non-deterministic software is enough. So, using Augustine's law and my highly scientific extrapolation of this graph, it's maybe an order of magnitude out, who knows, but it basically, if we look at that graph, the year 2050, we're potentially bumping up against a $500 billion per unit aircraft in 2050. Probably not quite as significant as Augustine's law, but that's a lot of money. And I guess the question is that viable? I don't think it will be. So what are we doing to try and correct that? Now, this data is obviously for military aircraft, which by nature are usually more complex than civilian. But I'm sure there's similar indications of civilian aircraft following similar tracks as well. So should we be trying to trade off some of our traditional deterministic software assurance efforts to getting the requirements right and potentially exploring the behaviors of the system and giving us more confidence through more exposure to the real world and more robust and high fidelity simulation? And potentially better methods of fast time simulation in high fidelity as well. If our whole purpose in software safety and software assurance is to explore the behavior and the responses of the system and software as thoroughly as we can, is this potentially a more cost-effective way to do it? Once again, trying not to be a heretic here and saying throw all the rest of it out. Somewhere in the mix there, I think, may be the right solution. All right, that's me. So thank you very much for your time. Hopefully I haven't run over time, but more than happy to take any questions now if there are any.